Imagine you are a teacher in a class of 50 students. You just finished grading their math test, and now you have a list of 50 marks. But looking at a long list of numbers doesn't help much. You want to understand how the class performed. Like, was the test easy, medium, or hard? Were most students around the same level? Are there a few students who scored extremely high or extremely low? To answer these questions, a branch of mathematics called statistics came into the picture. Now, instead of going through all 50 marks one by one, you need a single number that represents the overall performance of the class. To find this, we calculate the average, also called the mean. This gives us a central value, a quick way to understand where most students stand. We use this symbol to represent mean. But how do we find it? Simple. Suppose these are the marks of your 50 students. To find the mean, we add all these marks, which turns out to be 3550, and then we divide it by 50, which is 71. This tells us that, on average, a student in this class scores 71 marks. But this doesn't tell us whether most students are close to 71, or if some students scored really low, while others scored really high. For that, we need to understand spread. Now, let's think about how far the marks are from the mean. If every student scored exactly 71, then the marks would be perfectly centered, with no spread at all. But in reality, some students scored much lower, like 35, while others scored much higher, like 98. To measure this spread, we use something known as standard deviation. This tells us whether most students scored close to 71, or whether the scores are widely spread out. We use this symbol, which is called sigma, to represent standard deviation. But how do we calculate it? Let's break it down step by step. First, list all the marks of the students in a table. For the next step, we will subtract the mean score of the class from the score of each student in the class. This tells us how far each score is from the average. So, for student number 1, this will be 75 minus 71, or 4. Then for student number 2, this will be 62 minus 71, or minus 9. Then for this student number 3, it will be 82 minus 71, or 11, and so on. For the last student, it will be 74 minus 71, or 3. At this point, you might wonder, just take the average of these differences, and we will be done, right? The problem is that some values are positive and some are negative, and if we add them up, they might cancel each other out. That's why we need the next step. To get rid of the negative signs and make sure all differences contribute equally, we square each difference. So it will become like this. Now, all values are positive, and larger differences contribute much more than smaller ones. Now, we find the average of these squared values. Find their sum, which turns out to be this, and then divide it by 50 to get 255. We divided by 50 because we have 50 students. This value is called the variance. It tells us the average squared difference from the mean. But we are not done yet. Since the variance is based on squared numbers, it's not in the same unit as the original marks. To bring it back to the original scale, we take the square root of the variance. The square root of 255 is about 16. This final number is the standard deviation. In our example, the standard deviation is 16, which means that most students scored within 16 marks of the average. If the standard deviation were small, like 5, it would mean the scores were tightly packed around 71. If it were large, like 30, it would mean the marks were widely spread out. So, by calculating the standard deviation, we go beyond just knowing the average. We get a clear picture of how spread out the data really is. Now, looking at numbers alone is hard, so let's make a picture of the data using a method called histogram. A histogram is like a bar chart, where we group the marks into ranges, and count how many students fall into each range. In our class, only one student scored between 30 and 40, while 5 students scored between 40 and 50. As we move higher, we see that 5 students fall within the 50 to 60 range. The most common scores are between 60 and 90, where between 60 and 70 we have 9 students, between 70 and 80 we have 12, and between 80 and 90 we have 11 students. As we go even higher, only 7 students achieved marks in the 90 to 100 range. If we draw this as a bar chart, we will see a pattern. The middle range, 70 to 80, has the highest number of students, while fewer students scored very low or very high. Now that we have grouped the marks into ranges and visualized them in a histogram, we can go one step further and ask how many students scored below a certain mark. This is where cumulative frequency comes in. Cumulative frequency tells us the running total of students who scored up to a certain range. Instead of just looking at how many students fall within a particular range, cumulative frequency tells us the total number of students who scored up to a certain mark. To calculate cumulative frequency, we start from the lowest range and keep adding up the students as we move higher. In our case, up to 40, we have 1 student. Up to 50, we add the next 5 students, making a total of 6 students. Up to 60, we add another 5, making it 11 students. Up to 70, we add 9 more, bringing the total to 20 students. Up to 80, we add 12, making it 32 students. Up to 90, we add 11 more, giving us 43 students. Finally, up to 100, we add the last 7, reaching 50 students, which is the total class size. Now, if I ask you how many students scored below 80, you can easily see this table and tell me that 32 students scored below 80, right? If we plot these cumulative totals on a graph, instead of separate bars like in a histogram, we get a smooth increasing curve. This curve shows us the cumulative frequency, how many students have scored below each mark. Now, instead of just knowing how many students scored below a mark, what if we want to express this as a probability? Instead of saying 20 students scored below 70, we might want to say, for example, 40% of students scored below 70. This is where the cumulative distribution function, or CDF in short, comes into the picture. To calculate it, we take each cumulative frequency and divide it by the total number of students. It will become like this. For example, up to 40, we have 1 student out of 50, so the probability is 2%. Up to 50, we have 6 students, so the probability is 12%. Up to 60, it becomes 22%, and so on. Finally, up to 100, we get 100%, since all students have marks below or equal to 100. If we plot these probabilities on a graph, we get a smooth curve that starts at 0 and gradually rises to 100%. This curve is called the cumulative distribution function, and it tells us the probability that a randomly chosen student scored below a certain mark. The CDF is useful because it helps us answer probability-based questions. For example, if we want to know the probability that a student scored less than 70, we look at the CDF value at 70, which is 40%. If we want to know the probability that a student scored less than 90, the CDF value at 90 is 86%. If we want to find the probability that a student scored between 70 and 90, we simply subtract the CDF value at 70 from the CDF value at 90, which gives 46%. This makes the CDF a powerful tool for understanding how scores are distributed. Now, while the CDF tells us the probability of scoring below a certain mark, sometimes we are more interested in how likely a specific range of scores is. This is where the probability density function, or PDF, comes in. Think of the PDF as the smooth version of our histogram like this for our case. The histogram tells us how many students fall into each range, but if we want a continuous curve instead of bars, we get the PDF. Now, why do we need the PDF and CDF instead of just using the histogram? The answer is prediction. The histogram is useful for analyzing our specific class, but the PDF and CDF generalize the pattern. This means we can estimate probabilities for other students, even if we don't have their marks yet. For example, if another class of 50 students takes the same test, we can use the PDF and CDF to predict how their scores might be distributed. When we plot the PDF of our histogram, it is represented as a smooth curve instead of bars, forming a bell-shaped pattern. This shape is called the normal distribution. Even though our actual data might not be perfectly symmetrical, we can assume it to be approximately normal because it follows the general pattern where most students score around the middle, and fewer students score very high or very low. The normal distribution has two key properties. First, it is centered around the mean, the average score of the class. Second, it is symmetric, meaning the number of students scoring below 71 is roughly equal to those scoring above it. This pattern is not unique to just our class. It appears everywhere in nature and real life. Heights of people, IQ scores, blood pressure levels, and even certain economic trends tend to follow this same bell curve pattern. Now, why is the normal distribution so useful? The reason is predictability. If we know that the class follows a normal distribution, we can estimate student performance even without seeing all the marks. This is possible because of the formula for the PDF and CDF of normal distribution. Just plug the values of x, mean and standard deviation, and we then know everything about it. So, if we somehow know the mean and standard deviation of one class which follows a normal distribution, and if we came to know that most of the class follows the same normal distribution pattern, then we can find the related statistics of any other class without knowing the individual marks of the students in other class. Let us solve an example. A company makes light bulbs, and the time each bulb lasts follows a normal distribution, which means most bulbs last around the same time, but some last shorter or somewhere in this region, and some longer or somewhere in this region. The average lifetime of these bulbs is 1,000 hours, and the standard deviation is 100 hours. What percentage of bulbs last between 900 and 1,100 hours? So, can you solve it? The spread of the curve depends on the standard deviation, which is given as 100 hours. If the standard deviation is greater than this, then the curve will look something like this, but if it is less than this, then it will look like this. Now you know that in order to figure out how many bulbs last less than 1,100 hours, we will calculate the cumulative distribution function, or the CDF, of the normal distribution. For 1,100 hours, we use a statistics table or calculator to find the CDF of a normal distribution. We get this as approximately 84%. Using the same method, the CDF tells us that about 16% of bulbs last less than 900 hours. Therefore, to get the percentage of bulbs that last between these two values, we subtract 84% minus 16% equals 68%. So, 68% of the bulbs last between 900 and 1,100 hours. This is how we solve problems in statistics. So good!